So here's a 4-bit counter, and it's made with T flip-flops. And there's something special that I want to point out about these T flip-flops before I start playing with that. The thing to look at is the trigger here is configured to be it's a falling edge device. So that means when the clock goes from a 1 to a 0, that's when it will program. And it turns out that that is pretty critical in order to have an up counter, right? Something that counts upwards. So I'll leave that to you to experiment and try and see what happens if you have falling edge there. Maybe think about it and see if you can predict what will happen first. So anyway, what do we have going on here? Well, we've got the T input for all of these flip-flops to 1. So that means it's going to toggle every time it sees a falling edge. And so when this clock goes 1, the first flip-flop doesn't do anything because it's waiting for a falling edge now. So when it sees the 1 to 0, that's when it changes. None of these other ones have changed because they haven't seen a falling edge yet. But when this clock pulses and goes from 1 to 0 again, it's going to change this flip-flop here to a 0. So that means this 1 is going to go to a 0. And now this flip-flop will see a falling edge. And now we do it again. And so this guy has pulsed. And since this is a toggle flip-flop, means it's always just changing state 1, 0, 1, 0 with each clock cycle. So now if we get another clock cycle, that will cause this guy to toggle, and this will go from 1 to a 0, so that means this should also go from a 1 to a 0, and so that means we should also see this guy count up. So that's kind of how these counters work in a nutshell, right? You can get a little bit more advanced with them if you need to. But one thing I wanted to point out, and I said it in one of the previous videos, is you want to pay close attention to the labeling here. This is Q0, Q1, Q2, Q3. So, and I didn't address it immediately, and I probably should have, but this pattern probably looks a little off because it's backwards. This is our least significant bit, and this is our most significant bit. So this is just kind of a standard way that counters are shown, but it's just something to be aware of. So, right, we count, we start at 0, and so we see 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1, so on and so forth. And the other thing that's important to look at is this rollover here. So we're at 1, 1, 1, 1, and it's actually not super hardcore rocket science to figure out. If I toggle this guy, that's going to be a fall from 1 to 0. That's going to cause this to fall from 1 to 0, this to fall from 1 to 0, and this to fall from 1 to 0. And so that's how our rollover automatically happens. And that's why those properties with number systems is very important, because even though we might say that these are just the integers, right? We're just going from 0, 0, 0, 0, 0 to 1, 1, 1, 1, or we're going from 0 to F or 0 to 15, whatever it may be. That might not be the case, right? Maybe we want these to have some negative numbers, and so having the number system work with a clean rollover works really nice with this device, because this device is very simple and it has a number circle pattern. So there's nothing special that we'd have to do for our very desirable number systems like 2's complement and then regular unsigned integers. So yeah, so this is a basic counter using T flip-flops.